Ladies and gentlemen, hello and welcome to this edition of our global webinar series. Today's topic is about passive components for automotive car infotainment. My name is Alexander Nebel. I am Field Application Engineer in Europe and I will moderate the webinar today. We are very pleased that you find the time to join our webinar. Presenter today is Martin Ivanovski, our Field Application Engineer in Macedonia. With this information, I hand over to Martin. Hello, Martin. Thank you for your time today. Please tell us a little about yourself before you begin.
Hi, Alex, and good afternoon to everyone. Thank you for the nice introduction. As you said, my name is Martin Ivanovski, and I'm application engineer at KEMET Electronics. I'm in KEMET 2 years now, and I'm responsible for the web technical requests and sample requests for Europe, Middle East, and Africa region. For this webinar today, I have prepared an overview of what was considered infotainment back in the day and a sort of comparison with the present automotive trends. A short overview of the infotainment block diagram as well as the infotainment power distribution system. Then we will see a bit of comparison of the capacitor technologies, and finally I will talk about the comparison of inductor technology. So let's start. I wanted to compare a bit what was considered as infotainment in the past versus what is considered infotainment now in the, let's say, modern cars. And on this photograph you can see the interior of the dashboards of the favorite car of 007, 1964 model of the Aston Martin DB5. So if we take a look, we can see that we have some radio, some clock, few dials on the dashboard, speedometer, RPM gauge, some indicator lights, heating system, but of course not AC. For that particular time, it is quite sophisticated, but compared to the present, it is rather rudimentary. Nowadays, inside of a vehicle, you can see a ton of gadgets and whatnot. And on the right photograph is the interior of the Aston Martin DB11. Not the most advanced vehicle if we talk about the infotainment, but as a comparison to the older model, it will serve well. Of course, now we have full electric vehicles, hybrid cars, and so on, with a lot more gadgets on displays, but the DB11 is somewhere in the middle, let's say. So we have a lot more than before in terms of ADAS systems, lane assist, cruise control systems. Also, there is no more needles on the dashboard. Now it's full on display, which you can actually go on and program to do different things. So to sum it up, today cars have a lot more to offer than FM radio and speedometers. If you want to break down the infotainment system, we can go on and illustrate it using some simplified block diagrams. And we can start out with what we all know or historically have known as infotainment. That would be the audio section. So of course, the infotainment, the base of it, it's going to be the car radio, whether it's AM or FM or some other systems. It can also be concerning to your smartphone and playing your latest music that you downloaded on your phone. That would be the audio section, which would be the tuner and of course the Class D audio amplifier, which has a lot of passive components in there and critical requirements. There are, you want low noise because you want to have high fidelity in the audio experience in the car. But of course, there is a lot of other systems that are going on in today's infotainment system. If we look at the video portion of the block diagram, today vehicles have large numbers of cameras incorporated into the vehicle, whether it is for collision avoidance or backing up so you don't hit something, or lane departure. Also, you drive down the highway, you've got cameras looking on the right and on the left, making sure that there is no vehicles that you might accidentally bump. As you change lanes, there is a lot of different cameras in the vehicle. So you have got this video portion of the infotainment, which is taking all of these inputs and analyzing it, turning it into digital building blocks that can then be processed and making sure that everything is operating in safe mode. You know, you've also have radar systems that can sort of think of as a derivative of video. which are also sensing how far your vehicle is from other things. So that would be another functional block of the infotainment system. And of course, you've got the display portion. Back in the past, the display was the cluster of the dashboard, and it was consistent of speedometer, which was only a needle. Might have a RPM indicator, which was also a needle, and a couple of little warning lights, and that would pop up if there was a problem occurring. Today, the display is far more sophisticated. The analog to this would be the display of your computer screen. So the dashboard of the cluster of the vehicle is very similar to the display of your computer screen. And depending on the vehicle, it can be programmed to display a lot of different things, whether it's different set of information, or if you want to be green, make sure that the car is not emitting so much toxic gases to the environment. You can follow that information on your screen, for example. There is a lot of functionality going on with the display. So whether it is on the dashboard or on the center console, which would be the radio functions and tuning the climate control and all the other stuff. Also, you have nowadays you have on some vehicles entertainment system in the rear seats. So you've got that functionality in the infotainment system as well. And then at the heart of it all would be the controller. There's a lot of processing that is going on, whether it's figuring out what to put out on the display or taking the data from the cameras and the radar and manipulating it to go and figure out whether you are driving into the safe mode or to take corrective actions. So there is a lot of processing, again, similar to the processing that is going on in the computer that we are using every day. And then some vehicles have a heads-up display, which is a really cool feature. It actually projects information onto your windshield. If we look at the infotainment system, everything I have just described has again a lot of semiconductors that are performing all these functions, and they are of course supported by a large amount of passive components, whether this is capacitor technology or the magnetics technology or the resistor technologies. If we take a look of the communication aspect, besides all of those what we consider regular passive components, magnetic resistors and capacitors, we also have a lot of communications or RF passive components, the antennas or the plexers, which are differentiating between different high frequency signals, and those would be incorporated into the communication portion of the infotainment system. Now, if we want to see how everything is powered, the power distribution to all of these components, we have to start from the car battery, of course, which is a 12 volts battery, which is going to charge at roughly, let's say, 14.5 volts, give or take. So that is the starting point for powering inside of the vehicle. Your electronics that are inside the infotainment system, the semiconductors, they don't operate at 12 volts. They operate at a much lower voltage. So therefore, what we have to do, or what the designers do for the systems, they have to design what we refer to as a power distribution network or power distribution system to take that 12 volts and convert it down into the usable voltages of the semiconductors. The way this is done is using a large number of DC to DC converters, which will take 1 voltage and then basically chop it up at a very high rate of speed and then convert it to another voltage. And so if you take a look at a very simplified schematic of a DC to DC converter, over here we see the voltage coming in, and that will be the 12 volts, give or take, from the battery. And then the next step is as you want to go and decouple the converter from the 12 volt current, from the 12 volt car system. And the reason is when the switcher inside of the DC to DC converter is turning on and off and on and off over and over again at a very high rate of speed. What is doing, it is sucking in electrons and then stop sucking in electrons and then suck more and back and forth and back and forth. And this creates waves of disturbance that would go back into the car system that can disrupt other electronics in the vehicle, and should not be a good thing, of course. So what we do is we place a capacitor at the very beginning of or front end of the DC to DC converter to act as a reservoir of electrons. So it gives them up and take them back, and so on and so on. So it decouples the system, and typically this part would be ceramics or polymer technology. And it's important that this component be able to withstand what we refer to as a load depth. Then you are going to go through the switcher. On the output of the switcher, you want to go and have a nice, clean, stable voltage. So that is very friendly to the portion of the semiconductor that you are powering. And to do that, you create a filtering network, and that is going to comprise of two main components. That is going to be your inductor. It creates inertia for the electrons that are flowing, so it wants to keep them going up the same rate, so that your current doesn't change significantly over a short amount of time. It just keeps on going. And then, of course, it is going to be a bulk filtering capacitor that is keeping that voltage very stable. So you're keeping a nice current and you're keeping a nice stable voltage on the output feeding the load. So that is, I guess, the basic building block of your DC to DC converter. And that's within the infotainment system, you are going to have a whole bunch of these, supplying all of the various voltages to all of the semiconductors that are performing all the neat things in the infotainment system. And typically, the voltage is going to range from a little above the junction voltage of a transistor, so say about 0.8 volts, and all the way up to 5 volts. Now, when we take a look at all of these converters, they also need passive components going around them to support their operation. So we already talked about the input and the output filtering caps, but there is going to be more of those added outside of the functional block of the DC to DC converter. Typically going to be aluminum electrolytics, ceramics, or polymer technology, aluminum polymer or tantalum polymer. Those technology on the input and the output sides. We also need to monitor the voltage. So these DC to DC converters are closed loop systems, and for closed loop systems to operate, you need to have information related to the output, which in this case is going to be the voltage. And you need to feed that back into the functional block so that in the control loop, it can make adjustments to compensate if the output is varying beyond the set limits. Typically used in voltage divider using some precision resistors. We take the output voltage, run it through two resistors, and we top off the middle node and feed that back into the DC-DC converter. So now we have a feedback loop of multiple or division of the output voltage. And this allows the DC to DC converter to adjust the pulse width of the modulation. So it is going to reduce it if it needs to lower the voltage, or it is going to make it bigger, slightly bigger, to increase the voltage so that it can go ahead and maintain the proper voltage on the output. Also, you want to have some safety incorporated into the system. And so you want to monitor the current. So for example, if there is a subsystem in the infotainment system that develops a fault, you don't want to draw a massive amount of current and take down the electrical system in the car. You want to be able to kind of shut it off remotely, or at least that subsystem, and let the rest of the unit continue to operate. To do this, we are going to use a current sense resistor, which is very low resistance value, high current resistor, but it allows us to view the voltage drop across, and then from there we can calculate the current. And if the current exceeds a certain limit, then we can shut off that DC to DC converter and thereby keep the remainder of the system functioning. So there is a whole lot going on within the power distribution network to convert from the 12 volts that is in the battery being supplied to the electronics and the vehicle, versus getting the electrons to the semiconductors that are actually doing all the neat stuff that are in the infotainment system today. Now it will be really great if the capacitors were ideal and there is specific capacitor for a specific job, but that of course is not the case in reality. So what we have done is try to put together a table comparing the pros and cons of each of the technologies. Again, there is no perfect technology, so you need to take a look of the capabilities of the component versus the needs of the portion of the infotainment system. In the previous slides, I mentioned that the most dominant technology of capacitor used in the infotainment system and vehicles is the ceramic technology. And there is really two categories to the ceramic technology, class 1 and class 2. Class 1 would be the C0G, very, very stable, very close to being an ideal capacitor. The downside is that the electric constant is very low. It's like in the range of 30s, so you don't get a lot of capacitance out of those devices, but they are very stable. They don't change with voltage. They don't change with time. They are extremely long life, and they are also capable of extremely high temperatures. The class 2, which should be barium titanate, its base technology, those have a much higher dielectric constant, but they have more negative attributes. One of them is DC bias. You put voltage on the part and it loses capacitance. It is just a characteristic of the barium titanate and the dipoles and domains within the barium titanate structure. There is also this odd characteristic called aging. It doesn't mean that the capacitor is getting old. It just means that the capacitor is losing capacitance over time now, because the crystal structure of the barium titanate. Now the film technology, as we can see, it is as well very stable. When we talk in terms of capacitance, there is the benefit, of course, of the so-called self-healing property that the film capacitor possess. The self-healing property is exclusive to capacitors with metallized films, and it's their single best advantage. So self-healing is a phenomenon where in the event the electrodes are exposed to each other instead of the capacitor shortening, the capacitor repairs itself. This repairing of the capacitor is due to the thinness of the foils used. So when breakdown occurs in a metallized film capacitor, arcing causes the thin metal layer around the fold area to vaporize, and this vaporization process removes the conductive metal layer in the area around the flow. And since the conductive material is removed, a short circuit cannot occur between the plates. This prevents failures of the component. The reliability and operational life of capacitor significantly depend on their self-healing characteristic. Aluminum electrolytics are heavily used in both the input and the output sides because they have a big capacitance value. So they are typically used when you need much more capacitance value than the ceramics. The downside of the aluminum electrolytics is really narrowed down to two things. One is they tend to have a rather high ESR compared to the previous technologies that we talked about, and ESR is like the internal resistance in the part preventing the ability of electrons to go in and out of the capacitor. And this really ties to the fact that there is an electrolyte that is used in the capacitor, and this electrolyte has ions in it and that are in the solution, and they have to migrate one way or the other depending if it's being charged up or discharged. And because of the higher ESR, it has got this other characteristic we refer to capacitance roll-off, and it can occur at a very low frequency like 30, 40 or 50 kilohertz depending on where the ESR is, and that is all incorporated either in datasheets or design tools that we have at KEMET, and also they have a long life. I mentioned that they have electrolyte. which is a wet material, and this material is going to dry out over time during the operational life of the part. It's part of the physics behind the way the part operates, and we can go on and on about the mechanics behind it, but it occurs. And the life is very much dependent on the temperature, and we use a simplified equation where every 10 degrees drop in temperature from the rated temperature of the part, you double the life. So if it is a 2000 hour part at 125 degrees Celsius, and if you go to 115 degrees Celsius, it is going to be to last 4000 hours. So this will sum up the aluminum electrolytes. And those are heavily used in vehicles where you need much larger capacitance value than ceramics. Then you've got kind of a new entry into the market, and that is polymer technology. And there is a really two polymer technologies. You've got aluminum polymer, which are surface mountable chips, and then you've got tantalum polymer, and there is a lot of similarities between the two technologies. With the polymer system used as the cathode, the anode is different between the two. One is aluminum and the other is tantalum. But tantalum has the advantage of giving you a greater CV density than the aluminum polymer. The aluminum polymer does offer some larger capacitance values that you can't get with the tantalum polymer, simply because the parts are physically bigger, and you can also go higher in voltage in the aluminum polymer. Now the polymer technology, the advantage there is twofold again. The ESR is much lower because it is solid system versus a wet electrolyte system. So you don't have the ion transfer or ionic transfer going on within the liquid. It is a solid state system. So the ESR is much lower, and it can be in the same range as what you see for class 2 ceramics, for example. And you get more capacitance than you would get with the class 2 ceramics. So that is one advantage, because the ESR is lower. The capacitance roll-off, which occurs in all electrolytics, will occur at a higher frequency. So instead of rolling off at 30 kilohertz or 50, you are now capable of going well up close to megahertz range before you start to see that roll-off occurring. So that is a key benefits, and then the life, it is going to be much longer from what you see in a wet system. And the reason is because you don't have a dry out mechanism. It is solid dry system. So in the aluminum polymer, we used a simplified equation for every 20 degrees Celsius drop in temperature from the rated temperature, you are going to see a 10-time increase in life. So if you have 2000 hours at a 125 degrees capacitor and you go to, let's say, 105 degrees, you will have 20,000 hours operational life before your capacitor goes out of the limit for life calculation. And in the case of tantalum polymers, it is a little bit more nebulous, but generally, if you have 85 degrees capacitor or lower and you are 9/10 voltage or lower, you are going to see a usable life 10 years or longer. And again, it depends on the actual condition that the part is using. And the part number as a little factoid. Technology is heavily used in data centers that are actually handling the data for example, this virtual meeting, for example. And those data centers are running continuously, unlike a vehicle, so 24/7. And they are operating close to, in some cases, 19 or 95 degrees Celsius. So polymer technology is very robust for vehicles for bulk capacity. The legacy technology is MnO2 for bulk cap. This is also a solid state. It is using manganese dioxide as a cathode, which is a semiconductor, which is inherently more resistive than the other cathode system. So it is going to have, again, capacitance roll-off at a lower frequencies, very stable, but has higher ESR, and you have to derate these for reliability. You need to derate them 50%, and some additional derating because of the temperature. If you go above 85 degrees, this technology, it is used less and less in vehicles, platforms, and infotainment. And it's really because things have moved on to much higher frequency today.
Martin, sorry for interrupting you at this point, because I have an interesting question I want to ask now. Can you go one slide back, please?
No problem.
There was the question if you just can explain the frequency range. What is meant by low, medium, and high, just roughly in megahertz or gigahertz?
I'm guessing this is comparing about the capacitance roll-off, or
when you the second column, frequency, medium to high, medium low, low to medium, which range we are roughly? So for ceramics, you write medium to high.
Yeah. So yeah, for ceramics, you see, this would be in the megahertz to, let's say, I think megahertz to 10 kilohertz. This is exactly for ceramics, or to explain all the, or there's no info for. I'm asking if this is for the ceramic family or for all.
So in general, if you mean what is low, what is medium, and so today we
would say low
high frequency is gigahertz, for example, and medium is something in the 3-digit megahertz range, right?
Yeah. For example, up until the megahertz region, it will be, let's say, low from megahertz to 10 kilo, probably medium, and above that it will be high range.
Okay. Sorry, I said gigahertz. I meant megahertz.
Yeah.
Confusing maybe the attendees.
Yeah.
Okay. Thank you. You can all go on. Sorry for interrupting.
Yeah. No problem. Okay, so now if we want to see the role of the inductors in the infotainment system, we should look at them as if they are in two categories. We've got metal composite, and then we have ferrite. And then within ferrite, we've got two different materials. Let's start with the metal composite ones. So the metal composite, we are seeing that as a dominant inductor technology for vehicles, including infotainment. There is a number of reasons behind this. So a metal composite, let's explain the technology a little bit. What we do is we take metal particles, which are an alloy, and they are surrounded by basically a resin, which is an insulating material, and they are compacted or molded around a wire, which is creating your inductor. The inherent nature of this is you've got a distributed air gap throughout the entire structure, because you have all of these tiny metal particles that are separated by this resin. One particle is able to make an electrical contact to the next one. It's just like a gap, an insulating gap from one particle to the next one. So you have a distributed air gap, which creates a unique attributes for the device. The first one, it is that it inherently shielded your magnetic flux, isn't streaming out all over the place, which is a problem, or can be a problem, with ferrites. There is shielded and unshielded ones, but there is always flux that is escaping, which can create issues, of course. So your metal composite are inherently shielded, and then the second thing, it is that inductors have this thing called saturation. And what will happen is that the material saturates, and it's no longer able to go and amplify the magnetic field as your current decreases. And so therefore what happens is you'll see your inductance set at a certain level, and you hit a certain current, and then your inductance will plummet. And at that point, your inductor is not going to be usable in the circuit. I mean, it's still going to operate, but it's not going to provide the inductive performance that the circuit is requiring from it. So saturation is a big issue, and saturation of materials tends to be temperature dependent. The higher the temperature, the lower the current that it saturates. So metal composite, because of the way it is structured, with the distributed air gaps and the alloys that are used, we talk about a soft saturation. So Instead of the inductance doing this and then plummeting of the cliff at a certain current and temperature, what will happen is it will slowly and gradually drop off as you go up in current and also up in temperature. This makes it very ideal to design your power distribution scheme around, because no matter if the car is operating at minus 40 degrees Celsius or it's summertime and it's 35 degrees Celsius, we are still going to have nearly the same amount of inductance for the circuit to operate. And also because of the fact that it's got the soft saturation, we can design these parts to operate at higher temperatures. If we look at inductor used today in vehicles for power applications, right now the domain technology, and I expect this to continue in the future, it is going to be metal composite technology. The downside is they do have lower inductance values than the ferrites, and that is because of the distributed air gap, and then your efficiency is not going to be as high as certainly manganese zinc ferrite, and that is due to core losses. You've got losses from the wire, conductive losses, and then you've got core losses, which is from the current setup in the material. So that is metal composite. If we take a look at the ferrite, we've got manganese zinc and nickel zinc. The more dominant one that is used today tends to be manganese zinc, and the reason is twofold again. Number one is you get a higher inductance out of the material, and the second reason is the efficiency is really the highest out there. So you've got the lowest core loss in the material for manganese zinc. Nickel zinc is very good for core loss, but it is not as good, and you don't get as much inductance out of the nickel zinc. Both of these have hard saturation, so what happens is that you, as you go up in current, and this is again affected by the temperature, and then the inductance will fall down. So you need to design a system to have peak currents that below the saturation current at the maximum temperature that the system will be operating. Also, the Curie temperature of the manganese zinc is not quite as high as the nickel zinc. So therefore, your falling off a cliff will occur at a lower temperature than the nickel zinc ferrites. And then the last thing is insulation resistance, which most people don't really consider or worry about. But that is really the resistance between the conductor that is carrying the electrons and the core material itself. Metal composite, it's good insulation resistance, and that is really a function of the resin used to bind the particles together and the molding process. And then the ferrites can range from very good to not as good. And that is really a function of, I guess, the oxide layer that is forming on the surface. So that is the overview of the two main magnetic technologies that are used, metal composite and ferrite. And by large, metal composite, at least for power electronics going into the infotainment system, and most of the system in the cars are going to use metal composite inductors. And with that, I will conclude the presentation for today. I hope you found it interesting. Alex, back to you.
Okay, yeah, thank you, Martin, for the presentation. And we have reached also the 30 minutes, and we have still a few questions open. So the first question was already regarding the frequency, and please don't be confused by my first answer. We are not talking about gigahertz, but about megahertz. So when we talk about high frequency, it's all anything, I think, in the range of megahertz, and low would be something in the 1-digit kilohertz range, and anything in between is medium frequency range. Okay, and I guess the next question comes just for the last slides. What is hard and soft saturation? Maybe you mentioned it just in one sentence. It's not on the slide. Magnetic saturation, soft and hard. There's a third column.
Yeah, I think this is meant to the point of when I spoke about the when you reach a certain current, and then you lose all your saturation at once. Let's say that would be, let's say, hard saturation. And for metal composite, it's set in the table very good or soft. So this means that it will lose saturation gradually. So it will not be all at once, let's say.
Yeah. So it's let's say very constant for the metal composite and very linear, as where the manganese and nickel zinc have a drop at one certain frequency range.
Yeah. Yes.
The next question is also regarding the inductors. What is the maximum temperature of power inductor series? And this is a quite interesting question because we have a new series.
Yeah. I think that we have 125, but yes, I think there is a new series I'm not well aware of, but I think 150 or maybe more. Maybe you can help me on this one.
The latest series now offering is 180 degrees centigrade, which is quite new. The 150 or 155 is our standard series. So here, if you compare us also to competitors, we are slightly higher for the metal composite products. The new series will be 180 degrees, so much more higher. And for those who might think that this is not important for them because they are at lower temperatures, please consider that a higher temperature will also make it possible to have a higher current values. So this is not only for your own application. So if you have 100 degrees and you don't think you need 180, the 180 version will offer you a higher self-heating, and therefore you can put higher currents on the inductor, which is a good point for inductors, because the current flowing through the inductor is always heating up the component, and the higher the component can be, that is for you, and you can use a smaller component which is cheaper. So finally, it's a good way to use a high current, a high temperature product, because high temperature means high current.
Great.
Okay, and then there's is there anything to be considered regarding lifetime limitation of polymer capacitors? So I guess it's polymer tantalum capacitors.
Polymer tantalum, yeah, of course. If we talk about the tantalum capacitor, as I said, we need to worry about the derating, of course, which in the polymer, in the tantalum polymer, that is not the case. In the MnO2s, the derating is crucial for the life of the capacitor.
Okay. So great, and these seem for the moment to be the all the questions. If you have, to all attendees, if you have anything more questions, you can ask us directly or your local representative of Yageo, and we will help you with this. And with this, Martin, thank you for your presentation. Also, I like the technology comparison. And for those who are interested in the slides, we will submit them later on our webpage, and you can rewatch also the full webinar later on, either on YouTube, or the link is also on our webpage. So thank you, Martin, for today. Hope to see you soon again, and have a nice day.
Thank you very much. Bye-bye. Have a nice day.
Goodbye.